So this is our track.sagemath.org, which is the front page for SageMath development. And so this was recently reorganized and is now kind of the one-stop shop for everything you need to know about development. So we have two ways to participate here. The new and recommended way is to use your GitHub account. If you don't have a GitHub account yet, you can create one. And then there's a way to just log in to our track.sagemath.org using that GitHub login. And so those basically your username receives a prefix GH dash, which is of course for GitHub. Basically all new development users will appear with this prefix. We used to have our own account management, and so a lot of people who have been around for a while have these non-prefixed account names. This is not a cased system. It is just historically grown this way. So all users have the same rights on our track. And so the first step, of course, in getting closer to Sage development is you have to report a bug. So here's the initial information how to report bugs. And now we have lots and lots of tickets. So we are in the mid 30,000 right now, and so it's not so easy to keep on top of all of that. And so there are the various ticket reports that you can look at. So, for example, a good way to get started is to see what's around and what is waiting for review. So you can get a feel for what people are working on, and you can take a look at where you might help to give feedback to the authors and so on. So if you have been around for a while and you have forgotten about what you worked on 5 years ago, that's something that you can do here. You can look up. Oh no, for me this takes a while. Finally, there's a link to resumed this activity to create release notes for Sage. So starting from Sage 9.0, we have these collaboratively edited notes, and so this is something that we can do. It's a great way to stay on top of what's happening in Sage. Basically, can view the tickets that were merged, many tickets are small things, bug fixes and so on, but some bring major new features and so on, and it's a good idea to some kind of narrative so this becomes visible to users who want to stay on top of what's happening, but who cannot take the detailed look at all the tickets themselves. And so we have these release tours. So that's a way to see what's happening. Okay, yeah. So that's what we can see here, and I'm making my way to the mathematical software landscape. Oh yeah, here contributing by working on tickets. So this is where you find all the links to developers guides and things like this. And there's also some information about our development tools. Tomorrow we'll have a session. Tobias Dietz has worked a lot on bringing modern mainstream development tools to Sage, and so there will be a kind of tutorial on what's there. So if you have been around on looking through track tickets a long time, we've had this little thing here, which is the Sage patch bot, how the Sage patchbot advertises itself. But there are some of these new badges that have shown up, and tomorrow we'll learn a bit about these things. These are things that are run on GitHub Actions, so it's a good way to check, that the code that was contributed works correctly. Okay, so back to the mathematical software landscape. So this is a recently added table on our track, sagemath.org. And so this allows us to see what it is that we are talking about. So here in the left column, talks about what's in the SageMath distribution. And well, there are lots of things that are in the SageMath distribution. But in particular, what we have there is the SageMath library. That's what's appearing here. And so that's everything that fills the namespace sage.something. So starting from Sage algebras over Sage graphs to Sage topology. So which is the core, the Python, Cython written stuff that makes up Sage proper. So the SageMath library has integrated a few things that used to be extensions. There's the multi-year Sage Combinat project that was fully integrated in the early 10s. Then there's also Sage Manifold, which is fully integrated. Used to be an extension, but it's now absorbed. And so this table here is sorted upstream to downstream like this. So say these ones used to be extensions, so they used to be downstream from the Sage library. Now they're fully integrated, and on the upstream side, there are also a few libraries that are fully integrated now. We used to have a fork of the computer algebra, or more like symbolics package, GNAC, rebranded as PyNac. So this used to be a separate library. This is now fully integrated since sometime last year or 2 years ago or so, fully integrated into the Sage library. That has solved a number of packaging issues. And in the same way, packages GIAC Py and Sage Brial, which used to be separate, but which created issues with what depends on what. And so to resolve these issues, they have been fully absorbed. So these three rows here, they're forming the Sage library. And upstream of it, we have various other packages that are all included in the SageMath distribution. So we have Python packages, NumPy, SciPy, SymPy, CVX-opt, CVX-py coming soon, NetworkX, and so on. And then there are non-Python packages. There are many of them. Total is about 300 packages in the Sage distribution. And we're even packaging software that we don't make use of. This is either because it was added in anticipation or in preparation of later use, or there's some things in there that used to be used but are not anymore, and so they might fall out. So, for example, SymEngine is a system for fast symbolic manipulation that came from the direction of SymPy. Cocoralib is another commutative algebra package. ISL is the integer set library, which is, among other things, internally used by the polyhedral compilation technology in GCC. And so very new is CYLP, which is an interface to the CVC solver that is made by the CoinOR project. And then in the right column here, we have things that are not in the SageMath distribution. Of course, this column should be very, very wide. There are lots of things that are not in the SageMath distribution. We have, that goes in the direction of surveying the landscape. We have a number of pages that are kind of like a software catalog. And there are also external projects, in particular swmath.org, that keeps track of math available in the world. And so contributions that people can work on. So basically survey what is out there, what is useful, what can be added to Sage, what brings an added value, a good convincing integration path into Sage, and so on. There's also some software that we cannot integrate. There's obviously commercial software that we cannot integrate, that we cannot ship. There are the big M's that then there are commercial solvers. There are kind of solvers that are in the netherworld of not quite commercial, but also not quite open source, such as Skip. There's an integer programming solver with a strong following in the academic world, which is encumbered with a non-free license, academic free for academic use license, and which is therefore not which cannot be combined with Sage. But we do have interfaces to all of these things. They need to be separately installed and be available. So that's what's happening on the upstream. And then and another thing that's happening on the upstream side is Sage. When we build Sage from source, it can make use. So that's a trend that started in the Sage 8.x series, that we do not really have to build all 300 packages from scratch if the OS distribution already brings them in a precompiled form. And so we have a system that's called S-package configure that checks whether a particular system is present in the system in a usable form, so new enough version and not broken by neglect or broken by innovations on the packaging side. So if you find this to be usable, then we can make use of it. This can be disabled using arguments to configure. And so various distributions on macOS Homebrew, then there's Thunderforge, of course, various Linux distributions, Arch Linux, Debian, and so on, that we can make use of. Many of these things are automatically tested. So we test that in various configurations. Actually, the build succeeds and things test. Okay, so that's how we how distributions appear upstream. And then there's the downstream of Sage. So again, in the left column in the Sage math distribution. So downstream of the Sage library is software that makes use of the Sage library. Already this morning, well, it was morning for me. We heard about Sage Tech, also classic software to embed Sage computations in tech documents. And there are various Sage user packages, which can be a focus of this session here, that are independently packaged. But we also we want to work with the developers, so that we have some kind of improved discoverability. So what we do is we actually advertise these packages also as part of the Sage distribution. So we have in the Sage reference manual an automatically created list of packages. So it's grouped by standard and optional packages. Those user packages are optional packages, and other optional packages. But for example, what my example? My example was ADM cycles. So let's be here somewhere. And here it is. Also, we see here short description. There's a link to, in this case, to pipe.pi.org. So in this case, the only way to install this thing is, well, from PyPI, or using a shortcut, can do sage -i ADM cycles, and that pulls it from PyPI. So basically, by adding a little bit of metadata to Sage, we are not including a copy of that package. We are not pinging the version or anything. So this is basically just a way to improve the visibility of something, so that that is not hidden in the wall of 100,000 PyPI packages. But when people are looking for Sage math specific packages, that's the way to find them. So we used to have this kind of information just in the wiki, but things that are in the wiki are it's very hard to check that things stay up to date. Whereas when we have things as part of our source tree, so let's take a look at this one. How this looks in the source tree. Then we can also run automatic tests, for example, on it. So we can test that these packages still install correctly with the current version of Sage. And so this is something that we do run on GitHub Action. So let's take a look at so this one is our the main public facing repository, and so packages happen here in build/packages, and so that's a long directory list here, and so we can take a look at this package ADM cycles and see what's happening there. So just 4 files had to be added. So we have here spackage.rst. This is just title. Yeah, this is just what you saw formatted on my screen as well. What appears here in the documentation adds a few little details. Here it adds version information, and in this case, we are not pinning the version. It's just saying, well, we are pulling ADM cycles. That's what this file requirements.txt does. It connects this to PyPI. And so, yeah, that's a file that you see here, requirements.txt. That's all that a package needs in order to build this connection. And through the fact that we have it here, it will participate in our continuous integration that runs on every Sage development version on GitHub Actions. So we will get an error if it cannot be installed, and then just takes people to actually look at the logs to see if there's a problem. Now, we have not automated looking at the logs. So people need to look at the logs and see if something breaks, but that's all it takes. And then there are dependencies. So the situation here is that, of course, the Python packages themselves have a representation of their dependencies, but the Sage distribution only makes a weak use of these Python dependencies, but rather we have our own sets of dependencies are actually followed. And so here in this case, this package declares itself as only dependent on Python. This is a bit of a lie, and I have a ticket that fixes it for this package, because this one actually, it does depend on the Sage library. And so, for example, this one wouldn't be separately testable like this. And so I have I have a ticket somewhere. Maybe you can find it. Find it. Cycles. No, it doesn't look like I have a ticket for this one. Must have been a different package. Anyway, so we could create a ticket to actually modify the dependency so that it, yeah, and that would go into this file. Also, that's all it takes to add these packages. Gives immediate visibility to the package, and we have a meta ticket here. Well, that's not the one. We have a meta ticket somewhere here to, yeah, here. That's ticket 31164 that hopes to collect tickets that will add more packages to our catalog. So we have for example, here's a package. There's a nice value added distribution for a low dimensional topology that brings a number of additional packages. Center line is snappy, but also Regina is there, and so there are some tickets that hope to kind of make these things available in Sage proper as well. And we have also this wiki page here. That's the one that I used to collect these things, which is just human readable. It's not machine readable. And therefore, these packages are just listed there. They do not participate in our continuous integration. So we can take the information that is there. We can check that it's still correct after all these years, and we can add, we can create tickets that add this kind of metadata to Sage, and with the goal of integrating things in our automatically generated list of packages and combining it with the rest of the GitHub Actions continuous integration. I'll stop here for a moment because I've talked a lot already. So I'll take questions, comments, open discussion. Okay. Yes, I just opened the chat. Vincent, you asked, what about test suite of downstream software, such as ADM cycles? Would it be desirable to run them with the GitHub action at Sage? Yeah, okay. So I already commented on that. Let's take a look at the GitHub actions. It's happening here. Now, so if you haven't seen actions in action yet, it's happening in this tab here. And so let's take a look at what's happening there. So a few days ago, we had the new 9.7 beta 1 release. And so there's a handful of workflows that ran. So maybe you'll go through them. The main workflow for portability testing is this one here. It's called run toxini. It's not very enlightening, perhaps. And as we see here, currently everything is broken. So I fixed it already, but let's look at beta 0. Okay, so let's look at beta 0. So what's happening here in this workflow? You can see here on in the overview here, we ran 88 jobs that are labeled Docker. These are all runs on Linux variants. But then there were 84 jobs that test variants on Mac OS and some other little stuff. So these runs appear here on the left. So I'll skip Git pod. This will be explained tomorrow in the session on new dev tools. And then on the left we have various OS variants. So we have here Ubuntu Trusty, which is a trusty old version of Ubuntu Linux. And we run off all of these things. You can't see it right now because I've zoomed in too much. We run each of them in two configurations. There's the minimal one, there's the standard one. Minimal means that only the strict build prerequisites of Sage are installed. So that means GCC, binutils, Perl, just a few of these things. In particular, no Fortran compiler. And standard, on the other hand, includes all Linux distribution packages corresponding to Sage standard packages. So everything that is a standard package in Sage and for which we have an S package configure, that is a mechanism to recognize a suitable standard package. These ones will be installed. And so we test that we build correctly on it. Now, so because it is not true that the more, in general, it's not true that the more is installed in a system, that the easier it gets to build. Sometimes things get in the way because stuff can have incompatible versions. If one is not careful, can leak into the build and cause trouble. We have had a bunch of issues like this over the years. And that's why we are testing this in multiple configurations. So we have Ubuntu all the way to Jammy, which is the most current version. We have Debian going from Stretch to SID. We have Linux Mint from something wildly outdated to something current. We have Fedora from something wildly outdated 26 to current 36. We have CentOS in the incarnation of CentOS 7 to CentOS Stream 8. CentOS Stream 9 we have in preparation also. There's Gentoo, there's Arch Linux, there's OpenSUSE in both the Leap and the Tumbleweed variants. We have still have, this will go away soon, Slackware 14.2, Thunderforge. We have also some 32-bit runs, and then we have the macOS stuff. See what's happening here. So if you can see this, something ran for 4 hours, and we see here logs, installation of system packages. So this is a standard run. This installs lots of things. What's this one here? It's libfpll devel, some library and more libraries and so on and so forth. This all gets installed, but then we are running bootstrap and configure somewhere. So here we are running the bootstrap, and then things are ready for configure. So we are configuring it. And then we run a full build. So this is a non-incremental build. And taking this all the way to the parallel tests. So that's what's happening in this run. And so in this way, we can, that's how I make the tables for the portability of Sage that you see in the release notes. It's based on these automatic tests that run on each version. If we go back, you're back on the summary, and I go back to the list of the workflows. So we have another workflow that I look up here for 9.7 beta 0. And that is called test optional packages. Test optional packages here, and we do this for bunch of platforms as well. And so here you can see so this is running, for example, on an older version of Ubuntu Xenio. And so because there are so many optional packages, I've split this up into alphabetically, starting with digits or A through G, and packages H through O, and packages P. There are lots of packages with P because it's pi anything, and packages Q through Z. And so it's just building the packages, running them with sage check equals yes or equals warn or something. And so we see the run here. It's yeah, so these packages were tested 3 hours, 34 minutes. What is it doing? It's yeah, so this one is using what is called the maximal configuration, which means it installs even more. It also installs useless packages. It installs also packages that we happen to know about in the distribution, but can't necessarily use. This is, again, it's a test of robustness, that things that is present doesn't disturb our build. And then we are building the packages from Sage, and it just looks like a make build. So it looks like a make build with capital V equals 0, which means with reduced verbosity. For every package, I only get 2 lines. It's saying installing and then finally successfully installed, and it's collecting the logs. Yeah, so for example, here's BioPython. I don't know if anyone is using that, but there it is. So here's crypto minisat package that is in dire need of updating and maintenance on our side. And so whenever there's a problem with a package and there's an error, then we do see the end of the log file here. That's a standard behavior of build with capital V equals 0. And so if you want to see the full log, then there are various ways to do this. And so one way is to just stay in this interactive online thing here. And so there's a item here. It's called printout logs for immediate inspection. And that does that. Yeah, so it shows you, it just prints out all the failing packages logs. So you get here the full information, and this is automatically run for all the packages that we build. There's more ways how we can see this. Okay, let's take a look at what happened here, maybe in crypto minisat, to inspect what went wrong here. Yeah, and so of course we can just try to reproduce it on our personal machine, but there's a better way to actually do this, because this is all Docker based. And so we can scroll down to the bottom here, can do list Docker images. And so you see here, it did something. It offers us a name of an image. And so I can just go there. I can open a terminal, and I can say Docker run interactive with terminal. This one here, I want to run it with bash. And it's going to download it. So this goes to so everything that is being built goes to GitHub packages. Yeah, it's a container registry, also known now as ghcr.io. So we can just download this thing. Yeah, it's just a few gigabytes. Yeah, and so if we have a fast connection, we can just download it. Then we have it on our computer, and we can inspect what went wrong, and we can make changes and whatnot. So I'll move this out of the way. Maybe this will complete. So that's how we can debug such things immediately on the actual platform where it failed. Yeah, so that takes away the guesswork regarding portability work. Yeah, so in the olden days, yeah, so someone reported, oh, I'm here on I'm here on Debian stable with this or that package installed, and you know, we'd ask, you know, can you give us the logs? Can you give us an SSH log into your box so we can debug it and so on? Thanks to containerization, it's not necessary anymore. So the real workflow is you can reproduce users' system configurations by just provisioning it on Docker. We can then make this something that's automatically tested on every version. And when something goes wrong, we can just pick the failing container and then debug it locally. So if we go back to the summary here, we see there's also as an overview under this graph that I showed you before. There's also there's a little summary of what went wrong. So here we see, for example, the crypto mini set. It's telling us on Ubuntu Xenial, a crypto mini set failed, so that tells us a quick overview on what went wrong. So we might be interested in knowing, well, on what other platforms did the crypto mini set fail? I'll just do a text search for it. Okay, also failed on Linux Mint 18. Okay, also on Slackware 14.2 and so on. And so all user packages are tested in this way. So that's the side benefit of listing things with the Sage distribution in this way. This gets tested. I don't have a mechanism to monitor this. So I monitor it for standard Sage. It takes about an hour to sort through all of these things per 1 hour of hyperfocus to sort through these logs. I don't do this for the optional packages. So we need more people who go through the logs. But we have the tools. Hope that answers your questions, Marcin. We can't quite hear you, or maybe I can't hear you.
Yeah, let me remove that better.
Yes, now I can hear you.
Oh yeah. So we really have to go through the logs right now. There is no overview.
Well, there's here these annotations as GitHub Actions calls it. This gives you overview. Now you don't have to sort through the logs, but you do need to look at the test optional packages with Tox is the thing it runs, and you look for failures. Don't count the red check marks, the red crosses here. There, lots of things can go wrong. Lots of things time out and so on. But there's very specific things that we see here. Here, Topcom fails on Debian Bookworm. Yeah, optional package. Someone needs to take care of it. So.
Yeah, you did answer. Thank you,
William.
I'm amazed that this is possible. It's incredible. So, and especially given how long various parts of Sage can take to build and the resources required, it's extremely cool that you can do this with GitHub Actions. So one question is, are there resource limits that you're hitting that like paying GitHub might change? Is that how GitHub Actions works? Or do you not hit resource limits, or what's the situation there?
Yeah, so I should say, yeah, so Microsoft is extremely generous with GitHub Actions. We get these 6-hour runs on small machines, so 2 cores, and so a pro user on GitHub gets something like 40 or so machines in parallel. And so basically what we do is, we spin up 40 parallel jobs for all of these combinations, maximum of 6 hours. And so that gets stuff done. So basically we can do a full Sage build and test in 6 plus epsilon hours. So I have some tickets that for more robustness split up because there's stochastic variation there. Because of various effects on the server side, so I have a ticket to split this up into 2 parts. One first for the non-Python build, and then for the Python build and test, because there are some it's a good way to split it in the middle, so I do. Have a very sophisticated system of workflows for the Windows, for the Cygwin GitHub Actions, because it is extremely slow and it does not fit at all into these 6 hours. So if my computer actually agrees, then I can show you the CI Cygwin, what that looks like. Let's do this for the 9.7. Yeah, let's do this for the 9.6 maybe. Okay, there were some problems apparently, but anyway, it looks like this. So it's multi stages. We are using GitHub artifacts here to basically store a partial build as an artifact. Basically, just a big system of tar files that collect what has been installed already. There are 2 parallel stages, followed by 5 parallel stages, followed by 2 parallel stages, followed by 1 big integration stage, followed by some optional things like a test, documentation build, optional packages, and optional packages, and so on. So this one is split over, 7, 9, 10, 15 jobs of 6 hours, and that works reasonably robustly. What we don't have is, because GitHub Actions does not provide it, ARM64 runners for macOS. Nobody has those runners, and so that's one big limitation. Basically, we have 1 or 2 volunteers who have helped out with testing things on this platform, but what we would need is basically self-hosted runners for this platform or others. This is where having actual hardware would help. Of course, things. So the pipeline that we have for the various tests can also get clogged, and in general, having more runners than those provided by GitHub Actions would help for that as well. So this is where also having hardware would help. I personally do not touch infrastructure. So I've maintained servers during my PhD, and will not go back to doing such things. but people can contribute quite easily to these things by providing self-hosted runners. And then all of our GitHub Actions things, lots of things that we're doing now with GitHub Actions would benefit from that. But most importantly, have the ARM64 testing for macOS. Okay, so let's maybe move a little bit forward to maintenance and continuous testing of and deployment of user packages. I believe Jonathan wanted to show a few things. A little bit more. Yeah, I think that's
okay.
good.
Now that's difficult for me, but if that works for you, that's great. So where do we start here? So this is one package I needed for something else. Memory allocator. This started with started in Sage, and I just outsourced it as a separate package. And you can see that this is distributed, and there's not just a source distribution, but there's also nice wheel distributions for not everything, but a lot of things. So people that want to install this package, they will save a lot of time. I mean, it's a small package. It's like you get the idea. Maybe yeah. Here you need to build everything, and if you just download the wheels, and you don't have to build it, and it's done on whoever provides the package does it for you. And there is a nice workflow. See, I build wheel that does this for you. It's documented, and then has lots of combinations that you can see here. That's the most recent one, version 2.60, and you can even build a wheel for like the beta of CPython 3.11. Yeah, and here is how that works. So as you saw, that Matthias Köppe is responsible for pushing a lot of GitHub Actions to SageMath. So whenever I want to receive results quick, I just fork it, and then Microsoft will sponsor another 40 machines for me on my separate account. And this is just a copy fork of memory allocator package. And I just have a pull request, and then on pull, it runs this wheels. It's a file this corresponds to. No, that's just main. And then there is build wheels. Yeah, and it's a really tiny file. So it's super easy. It's just copy paste, and there's not much to do. Yeah, you can modify the version, and there's a couple of here. It tells you that there's a couple of environment variables that you can play around with. I never did that, but you could do that. For example, if you want to have the beta Python 3.11, then you need an environment variable, and you can play with that one. And that's pretty much it. The other thing that I'm also doing here is I'm automated the source distribution building. In this case, it's kind of useless. It's just so that I don't forget it. And but this might be useful if you have a package that does some auto generation or something. Yeah, and then it happened to me a couple of times that I forgot to auto generate and upload it, and it's annoying for everyone. Yeah, and if you have a workflow, you can just make sure that this doesn't happen. Yeah, you could do that auto generating in that workflow, and then every time you do a distribution, you don't forget that you have to do this. And the reason why I have it here is that I don't include my personal files in the source distribution. Yeah, so this is a clean GitHub tree, and not my personal one that contains, I don't know, like the compiled files or whatever, and something that's embarrassing. And if I do it on the GitHub workflow, then I don't have to worry about it, and it's not there. And it takes, and it Well, here you see it runs on Ubuntu, some Linux. Yeah, and that's what GitHub does in macOS and Windows. And that's the last one. That's really quick. I mean, what is it, 1 second or something? And that's the Ubuntu one also only took 8 minutes something. Yeah, and then it just generated all the files. And now problem is you can't really see that. So what is it? So that's the build wheels, and because I only share the screen now, you cannot see what's all in that artifact. It uploads an artifact, and this contains all the files that you need to include for your distribution to PyPy. Yeah, and one thing you can do, you can just, it says up here, and also whenever you create a tag, so you can first create the tag for your new release, and then it generates all that stuff. And then when you do your release on GitHub, whatever, then you can just drop the files there for the release. Yeah. And that's pretty much it. And it's, as I said, it's very easy. And yeah, somebody came up to me and told me, okay, can you please provide wheels? And I didn't know how to do it. And then he said, oh, you can just use this, and it's super easy. Yeah. And it kind of makes life easier for people using your packages. So I can, yeah, I don't know. It's not that interesting. The artifact contains exactly, or now a bit more than what you see here. Yeah, and the new version, of course. All those files are in that artifact. And then you can download it and put it in. I put that then manually. That's probably not the best workflow. I put it manually in my dist folder, and then I upload it to PyPy. Yeah, you can also give your PyPy secrets to GitHub Actions if you feel safe about that, and do that all automatically. But I wouldn't do it personally. Okay. As I said,
thanks a lot. Thanks a lot.
It's easy, and it's a quick story. Do you have questions about that?
It isn't indeed. Yeah, so it has streamlined a lot. Yeah, so it's pretty easy to set up for a package, and so now I guess the task is that many of the packages that are kind of in the kind of maintained by Sage people, either upstream or downstream, they would benefit from having such infrastructure, so that things become easier to install. For example, upstream, yeah, libraries such as PPLPY. Also, they would be that would be easy to. The great thing about cibuildwheel is that it has it uses a mechanism called audit wheel on Linux that makes sure that all shared libraries that are needed are included in the wheel. So they call it repairing the wheel, but it's really the trick that makes these things independent now by means of preparing the self-contained binary distribution of the thing, independent of system installation of the underlying C++ libraries, and so that it gives a great benefit to deployment. Now users can install this without having to touch non-Python package management tools. So how would you install a PPLPY? We would first have to install PPL either through the OS manager or from source, and then install PPLPY building from the source distribution. But by having these pre-built wheels for all supported platforms, the user can just pip install the thing. Now, and so this just completely changes the game of who can use these things. Everywhere, in any cloud computing environment, you can just do the pip install, and it will just work. And it's super fast. And basically, what I would like to suggest is that in particular for packages that downstream from the Sage library doesn't quite work yet, because we still need to work on actually doing these things for the Sage library. But for everything that's upstream of it, like a Jonathan's package here, and Vincent's PPL-PY, and many other things. So like ciPari or ciPari2. In particular, the split between ciPari and ciPari2 is exactly motivated by whether pari is bundled or not, to my understanding. I think we can unify these two packages by taking the viewpoint that bundling the pari library is really just the repairing of the package by this implicit action of cibuildwheel. That just includes the necessary shared library with it. Maybe a little bit of custom if they have data files, but that would be my hope, that we can basically unify these two packages and make them both installable within a second.
And there's an issue for this, as you mentioned.
Yes, there are issues.
Yeah. Okay. And here is an example that this is really powerful. Yeah. I mean, NumPy is big. Like it works not just for tiny little packages, but also for powerful packages. Yeah.
Right. Yeah. So NumPy does it. NumPy has millions of users, and so we should do that too.
And it just works out of the box for them. Yeah. More or less. Okay. Other question?
I think they have a pretty complicated setup because they bundle OpenBLAS, and so they may need to make sure that this is binary compatible, but not architecture pessimized. So they do build it with in a dynamic arc kind of way, that just runtime dispatch to the platform and stuff like this.
I mean, yeah, they have a lot of things to take care of. Okay, so but it's not Wheels CI, like it's not their fault. Like the CI build Wheels, that it's difficult for them. Anyway, should I stop sharing on the screen, or do you want?
Depends on what the next question is.
Yeah, are there more questions?
It's related to these wheels, but not directly to what you talked about. I raised some issues with this bundling of C libraries. So for example, PPL-PY, it does depend on GMP. So if we do a wheel for PPL-PY, it would bundle GMP and PPL-PY, correct?
So let's see. So GMPY2 would only be an install requires, so a runtime dependency of PPL-PY, but both of these distributions, which are both installed as wheels, would bring their own copy of the GMP shared library. That's kind of the weird thing about wheel building. Yeah, so everyone brings their own shared libraries, so they're not really shared. And
but
so,
how would that? Yeah. So the issue I raised in the
it can only possibly work by the fact that these things are ABI stable. Yeah, so it couldn't possibly work if so GMP, of course, has a seldom used way of configuring, for example, how many how many digits, so how many nail, you can build it with nails, right? The GMP, and like you can make non-standard configurations, and obviously these things won't be API compatible, right? If you create one GMP number in one version of the library and one GMP number in the other library, they just don't fit together twice, right? So the assumption there is that everything that you do in your system is using kind of standard configuration of the libraries, and only then it can work. Yeah. So, yeah, I don't think anyone uses GMP in non-standard configurations these days. I think this was a thing on people using this on UltraSpark, where there were some tricks that you could play with the tag bits, but on today's architectures, everyone uses the same API for GMP. So everything is in the same format. So it just fits together.
So what do you do when there's a API incompatible change?
I suppose it is a problem for the people who are doing the binary building, and yeah, so.
But I mean, how do you encode a dependency, right? So something downstreams.
It's not. Yeah. So Python does not know about such things. There's no mechanism to, for example, declare dependencies on non-Python packages or anything like this. There's a PEP that tries to encode these things so that there's at least there's a field in the wheel that can encode such things like dependencies and ABI variants. But as of now, it's basically just you build it, you test it, does it work or does it not work? And so that's the story about.
Okay, basically, so the strategy is if it eventually fails at some point, and it would just tell people, okay, just wipe it, reinstall, and then it will work again. I mean, which is fine, I think. I'm just asking.
It's that's the state of the art in Python packaging right now. So you have the wheels. You can declare what can you declare? You could declare the arc. You declare the OS. You declare the Python version. Yeah, and so compatibility is determined like this. There's no mechanism for other things. Yeah, in particular, there's yeah. So you can also locally build a wheel. Yeah, so we have changed the Sage build system in particular. So that it goes through wheel building. These wheels, they are not repaired. Yeah, so they do depend on locally installed shared libraries. Yeah, so if you try to ship them from your computer to the next computer, they just won't work, right? Because they have unresolved or broken shared library dependencies. Yeah, but they are still useful if you want to provision, for example, venvs. Yeah, so if you want to create a fresh virtual environment for your Python stuff, you can just install these locally built wheels, because yeah, the shared libraries are still in the same place, right? But there's no Python mechanism to be disciplined about these things. That's kind of, it's out of band information. Yeah, there's a PEP to fix it, but it won't happen before 2024, I think. More comments?
Yes, I did not raise my main concern. So about PPLPY, the real problem will come if I want to use it in Python, because at the time I link with PPLPY, it links with its own GMP, but if I need GMPY2 at the same time, there is another GMP it will want to link to, no?
Yes, both packages bring their own copy of libgmp. That's what the audit wheel step does, and macOS there's a comparable mechanism. So they do the binary patching of the ELF, yeah, and to update the the embedded path of these libraries, and copy in a copy of the GMP to your wheel, and that's how it works. That's how NumPy brings its own OpenBLAS, and so that's also how you would bring your own copy of GMP. Now GMP Y2 would do the same thing. It would bring its copy of GMP. Yeah, so now one has to rely on it on these two things being ABI compatible. Yeah. When you
I don't know which GMP will be used in the end. How do I know which GMP will be used in the end? If I have a Cython project which uses at the same time GMP Y2 and PPLPY?
Well, it is system dependent.
Yeah, this is very not.
Yeah, so you don't have a very good control over that. It depends on. Yeah, so in particular, if you're like, let's install a random wheel that comes from somewhere. Yeah, it's kind of a undisciplined way of doing these things, and there's no guarantee that it will work. Yeah, and so that's for example why in the Sage distribution we do not use wheels. Yeah, so we have a full source build. We make our own wheels. And so we have a set of our own compatible wheels. We're not taking any from PyPI because there's no centralized control over, that these wheels fit together. Yeah, our set of wheels is consistent. Yeah, but it also these are not repaired wheels, but rather they refer to shared libraries in the system, yeah, or in the Sage local, But the wheels that you would be building are using CI build wheel and so on. They would bring their own copies of the libraries, and one has to rely on the projects doing a good job in quality assurance and documentation of what is it that they do. Like for example, what processor architecture variants do they support? Yeah, what's like the minimum supported architecture? Is it going to try to use AVX2 or instructions? Yeah, so there's no place in the file name or the metadata of wheels to encode that. Yeah, so it's out of band. Yeah, so you need to rely on people doing a good job in defining first of all, and then checking and building accordingly. Yeah, but automated tools such as CI build wheel at least give the confidence that the wheels that end up on PyPI are not the result of a random system configuration of the day that developer 7 had on their computer in November 2023. Yeah, so so that's I think one of the great contributions that CI build wheel brought to the Python packaging world. That's not random stuff that developers upload, but this is a streamlined process that people can set some trust in if they feel comfortable to do so. Okay, more comments? Did anyone bring their packages? Yeah, so we can continue with these things later. Maybe also organize this in the Zulip. If there's any interest in hands-on activity, I'll be happy to help. So I think on our schedule, we have that I say a little bit about a modularization of Sage. So I'll talk about modularization of the Sage library. So this is a project that I proposed some 2 years ago, I think in May 2020. And it's motivated by the observation that a lot of the explosion of the scientific Python world comes from the fact that things are easy to install. and easy to combine. And projects such as NumPy are everywhere. And you can install them by just typing pip install. And it takes like 3 seconds, and then you have it. Whereas in Sage, we have the problem that it has accumulated a lot of dependencies. Full installation is something like 10 gigabytes. Compile from source takes a couple hours. If you have a powerful machine, you can do it in an hour. But it's difficult to deploy in this way, unless, of course, you're operating in a cloud computing environment where this is already provisioned. Yeah, despite such deployment and despite the successful work of downstream packagers, such as, and so here I'm referring back to this page here. So downstream of the Sage library are not just the Sage math distribution, but also various other distributions that carry Sage math, including CondaForge. And yeah, so the packagers have done a great job, of course, to make Sage available, but I still hold that essentially for lots of applications, if a package is not pip installable, then it basically doesn't exist. So because other packages are unable to use standard Python means to declare a dependency on them, and so one always has to jump out of the system to make sure that it's available. And so this is something that also our Sage users have been struggling with when building their own Sage user packages for distribution. It's kind of impossible to even declare a dependency on Sage. So there are lots of workarounds that become necessary and so on. And so overall goal of the project on modularization is to make Sage more easily deployable in applications. And the observation there is that probably most applications don't need the full power of Sage and its multitude of libraries that it pulls in. So Sage itself has something like 4,000, 5,000 modules. That's one thing, but it also brings these gigabytes of dependencies on compiled libraries, and those are that bring a lot of the weight. And so what is needed is to somehow make sure that we can install and run parts of Sage that do not depend on all of these compiled libraries. Also, if I want to do manifolds, I do need symbolics. So I will need maxima. I do need Pynac, which is now integrated in the Sage library, and so on. But I'll probably not need some high-level number theory libraries. Yeah, I shouldn't need Pari, for example. And there's also very little use of, for example, the LL algorithm for lattice basis reduction in manifolds. So basically tightening such dependencies, that's the idea behind the modularization project. Okay, so let's see where I should start. So I'll start with sharing some drawings so that you know what a Sage installation looks like and what its organizing principles are. I'll do this as quickly as I can, but it's some necessary context. I hope this is visible enough. Can you all see this well enough? So I'll zoom in a little bit more. So here's what Sage installation looks like from the old days, since about 2015 or so. There's a source tree, then there's a directory that's named build, which contains the infrastructure for the Sage distribution. So this one here is essentially Sage library. And local was the hard-coded installation prefix. And it kind of still looks like this today, except that recently we changed some defaults. And to get it back like this, today we need to pass the argument without Sage venv. I'll explain this in a moment to it, and then it goes back to this. Okay, Sage 8.0, it became possible to actually configure an installation prefix. So what is known as the variable Sage local, this now is configurable in the standard autoconf kind of way. So we can do configure prefix equals arbitrary directory, and then local is no longer local, but is in a directory of your choice. This is where the installation goes. So this is where the Python goes. This is where the non-Python packages go, and so on. If one passes a prefix, then this now implies this thing here. It implies without Sage venv, and everything is nice and self-contained in this configured Sage local. What is new is we have two symlinks in the Sage root for convenience. One is called prefix, that's the configured prefix, and one is venv, which is the same. So, but they both link to Sage local, so this is where you find your stuff. Okay, so everything is still monolithic. That's the old way how the Sage distribution was done. But since Sage 8 point something, Sage makes use of these system packages, so it becomes important what is also in user or in other system locations. Using S-package configure mechanism, we can refer back to various things, and we don't install them in bin. So we are basically cutting through to the user bin and the user lib for useful system installations of libraries and programs, including, and so that is one of the newer things that happened at the beginning of 2020, is that we can also make use of system Python 3. So we can make use of system Python 3. Needs to be a non-crippled version of Python 3. 3.7 to 3.7. Soon we are getting rid of 3.7 and only allow 3.8 and higher. And so what we are doing is we are building a virtual environment over that system Python that actually ignores side packages. In this way, we are relatively isolated, but we do make use of the system Python, so we don't have to build our own copy. And so then this here is just a symbolic link. Some platforms a copy of the Python executable, and there's a magical file called pyvenv.cfg that makes it known to this Python here that it is actually it's a virtual environment Python over system Python. We still install our own side packages. So this is where all our Python packages that we install go. They go in here. All right, so this is a situation since Sage 9.1, we find and make use of a system Python. So if you want to use a particular Python, you can use configure with Python equals something. You can select the Python of your liking. It will reject it if it's not suitable. Yeah, so you need something that on Debian, if you only have a minimal installation, you lose, and our configure script will tell you that you cannot use it, and you either need to take action to build our own copy of Python, or it will tell you what package to install on your distribution to make a proper Python available. So this still looks like this, and so we still have these two symlinks here from the root through venv and prefix pointing to stage local. Okay, what's even newer is that we have a decoupling of the non-Python parts and the Python parts. So that's now color coded. The non-Python bits, they are in blue here, and we have in green part the Python bits. So all packages nicely fall into these two categories. And we only have dependencies on things that use Python, on things that don't depend on Python, but not the other way around, except some packages needed at build time for some scripts, but that's the runtime dependency situation. So things depend, so the green stuff depends on the blue stuff. And so we can now keep them separate. And this has multiple benefits. So this is now represented by these two diverging symlinks. Configure configures the pair of sage local and sage venv. Sage venv, the name of it is automatically determined by default. It lives somewhere deep in here, somewhere deep in sage local, in a path called var lib sage venv something, depending on the Python version. We have our default location for the venv, and because it's so deeply nested, I created this venv symlink, so it's not so hard to find. Also, you have run.configure. After that, you have these symlinks. This is where stuff is. Yeah, so in this way, you can always see what's happening. And now maybe you built it like this. Maybe you did the configure prefix equals sage local with Python equals Python 3.9, and then with the sage venv. This with stage venv is necessary to do this separation if you provide a prefix. And then it looks like this. And then maybe you want to test that something works on Python 3.10 as well. And now the trick is you can just reconfigure. Same prefix. Just change from with Python equals Python 3.9 to with Python equals Python 3.10. And you'll get a separate venv. It shares the same sage local. Yeah, so in this way, you don't have to rebuild all of that stuff. Yeah, so all these heavyweight compiled packages, you compile them once. You just configure things. It changes the venv symlink, just for the users, not necessary for building or at runtime over here. And so you now have a version with Python 3.10. This one here will still work. So the build, so everything that is in sage venv together with the sage local is self-contained. You do not need that sage root is synchronized with it. Yeah, so it's just a working installation, and it will continue to work unless you somehow make the sage local out of sync with the sage venv. Then things can break. But in this way, you can cycle through during development through different versions of Python to make sure that stuff works without having the burden of the duplication of the sage local and so on. It's very helpful for development. And we can also decide where stuff goes. We can say just a custom venv, and then it just builds the Python bits in wherever you want this. It still refers back to the sage local. There's a mechanism how the venv knows what the sage local is. There's a little Python module called sageconf. I need to zoom in so you can see it. It's here. Sageconf knows about the name of sage local. That's where stuff finds it. That's used to set some search path and stuff like this. And then in the background, there's still the user directory, so system installations. Still, we make no use of side packages. Okay, so that's what an installation looks like. Now we can discuss how this installation comes about. So let's take a look at the Sage source tree according to current standards. So it looks like this. I've already mentioned build and source. So it's here, build. This is Sage specific. This is the Sage distribution and all of its infrastructure. Earlier, I mentioned build packages. Yeah, so this is where we have Sage specific metadata and scripts for the various packages that make up the Sage distribution. This is where you would, if you want your user package registered, this is where you would add a directory and a couple of files. There are some packages that are serious. We call them normal packages that come with, there's a pinned version. There's actual checksum information with link to the upstream tarball dependencies. There's an install script. There's possibly an package configure script. And there's also information about equivalent system packages. So this is how we give advice to users that you don't need to build GMP because you are on Fedora and you can install libgmp devel. Yeah, so this information lives here in this directory for every package. And so this is how we inform the user, and this is also how we provision the continuous integration environments in a convenient way. Same thing for Python packages. Yeah, for normal Python packages, we have install script, we have tarball information, we have dependencies kind of duplicated from the Python metadata package version, stuff like this. We don't have package configure really because we cannot make use of system Python packages. We have our own VN that doesn't use system side packages. Okay, and then there are more Sage-specific packages, such as the Sage library. Sage library is a package. This one is not a library. This one is not a normal package. It doesn't have a checksums.ini file because we are finding its source tree not in some tarball, but rather the source tree is embedded in our big mono repository. It lives somewhere deep in SRC. So this is SRC is where all the Python stuff lives. But what is new is in between there's a layer that is called packages. And this is now where we have several directories where pure, not Sage specific Python distribution packages live. So stuff that has a setup PY. Well, if you learned about Python packaging some 5-6 years or longer ago, you're invited to actively erase all of that from your memory because Python packaging has changed in a multitude of ways, and it's best to relearn from scratch. The big new player is PyProject Toml, which has the build time information. It tells you the build time dependencies of a Python package. It tells you what system is used for building. It's not everything is setup tools these days, but it's just declared here. You can bring your own build system. There's a large range of clean build systems for various purposes and so on. But we are still using setup tools for all of our purposes. So there is still a setup PY, there's also setup CFG. And so we have a package here that is called SageMath Standard. So this is the name how also Sage appears on a PyPI. So if we look for SageMath, we do see a bunch of packages here, and the Sage library is represented by this package here, SageMath Standard, and there it is. So it is kind of, sort of pip installable already, but more on that later. So where does it come from? It comes from this directory. So we have a workflow that on GitHub Actions, on every on every tag takes this directory here, does a build of the source distribution, and pushes it to PyPI. That makes the package Sage math standard. Now, I said this one has a, it needs to have Sage sources in it. Well, it doesn't really have it in there. It in our source tree, it only has a symlink to where it actually lives. So lots of symlinks here. It points back to the traditional monolithic source tree of Sage, just SRC. So SRC, Sage, and under Sage, now you find this whole thing, from algebras to Sage tensor and so on, all living in here. And modularization is not going to change that. So everything still is monolithic. It's mono repository, but also mono source tree. So you still have the monolithic source tree. So if you want, as a Sage developer, you want to make changes to the Sage library, you do this by editing stuff here. So modularization is something that's happening here, and developers do not need to be aware of it for making just normal changes to the Sage library. So modularization happens by building Python packaging metadata on top of this monolithic source tree by picking and choosing parts that go into one distribution. Sage math standard is still huge, and it has the same dependencies that the Sage library has in the distribution. It's really just the name for it that we use on PyPI. There are a bunch more of such pip installable packages. There is Sage setup, is the build system of based on setup tools for the Sage library. It's now also it's a pip installable package, because we will have several pip installable packages that all use this thing as a build system. So they are not duplicating it, but they're just pulling it in as a declared build time dependency, as a something declared in the pyproject.toml. So someone should probably work on this project description here. Yeah? Okay, so so that's Sage setup. Then there's a thing, SageConf. I've mentioned this already. This is somehow that builds the connection to Sage local to the system. I'll not mention this now. So now what's happening in the modularization, we'll have more of those little directories. So this one here is monolithic, will remain unchanged in structure, except for minor adjustments where things were particularly hostile to modularization. So we have made lots of changes already, and I'll show you a little bit the project page for that. So that is happening all on MetaTicket 29705. Started 2 years ago, and we made lots of changes. Started to get merged in Sage 9.2. What's happening? Some build system work. Basically, make the setup PY shorter by factoring things out to this Sage setup thing. Then there was a wild thing called optional extensions and a hard-coded list of extensions. We got rid of this, replaced this by discovery. So more in the way that Python operates uses find packages instead of listing packages. So there's a discovery things are happening also for Python modules. There's a new mechanism that I'll explain a little bit that's called namespace packages. And so that's pretty much what drives the modularization in this friendly way for developers that allows us to keep both the source tree and the corresponding a namespace, meaning what do I import, like sage.geometry.polyhedron.base. This is not going to change. So this was designed to give a nice structure according to mathematical fields and categories. Sage.rings, sage.algebras, and so on. This is not going to change. But these mathematical fields, they are not compatible with ideas of modularization. So where does the pressure for modularization come from? It comes from the dependencies. Just because something is a ring, doesn't make it have similar dependencies to another ring. But there are some rings, there's the p-adics that use NTL, for example, Victor Schoep's number theory library. But there are other rings that have other library dependencies. So the modularization has it's cross-cutting in respect to this nice namespace that has been designed for organizing Sage. And now this is where these namespace packages. So these are there's a PEP, a Python enhancement proposal that was done that introduced what is called PEP 420 implicit namespace packages. There were earlier incarnations that were kind of clunky, that worked in Python 2 as well. This is something that was merged sometime early in the Python 3 series, implicit namespace packages, and they are really convenient because how do you make a namespace package? Basically by deleting the init.py file. That's all. So you have an ordinary package, and so here one needs to I need to editorialize a little bit. The word package is, of course, heavily overloaded in usage. So when you say I pip install a package, the technical word for that thing is a distribution or distribution package. And so these are the modules that I'm referring to when I'm saying modularization. What I want to do is I want to split up the namespace that is formed by the Python packages. Our packages are the directories that contain the modules, such as this one here. I want to split this one up into different distribution packages so that this distribution, these little smaller distribution packages, can be relatively independently installed and individually have much fewer and lighter weight dependencies. But the layout of these, what is in such a distribution is not aligned with this hierarchy that forms the namespace. So the hierarchy of these nested directories or packages. So, but as I said, we still have these normal packages that have init.py in it. But then we add to it namespace packages that don't have the init.py in it. And so PEP 420 tells us, well, if you want two distribution packages that are providing portions of the same namespace, for example, let's look at sage.matrix. What's in sage.matrix? Well, we have different implementations for different base rings. So here we have something for mod2, Z2 somehow, in the dense implementation. It depends on some library. I forget which one, maybe Flint. And then there's this one here. So this one here, this one has a compile time dependency on the Flint library and the runtime dependency on it as a shared library. This one here, that's a more specialized one. It's provided, it depends on a library called meatx. It's a more specialized one for some GFP power n dense. So provided by an optional package. This used to be one of those optional extension modules in Sage. But now the idea is we don't want to have a global dependency on MeetX. It's something for a more specialized use case, and only people who need this kind of stuff should pull this in. So what are we doing? We are designing a distribution that provides this portion of the namespace. And so this will end up in something that will look like this. So we have here an sdist, a source distribution. This is what will be shared on PyPI. So this one here goes to PyPI. It will be pip installable, and well, we'll have a setup py, I guess, and a PyProject toml, and then it provides this namespace. It has Sage matrix gfp and dens pyx. So the Python file here, Python source file. And it also has a corresponding library bindings. It's another Python source file, meetx.pyx that lives in sage.libs.meetx. So it's something that you would import or C import from sage.libs.meetx. So the namespace view on it is, well, there's a module here that lives in the package sage.matrix. But it will be provided by the distribution package that we give some name. Maybe we call it sagemath-meetx. So we will be using this prefix sagemath- according to a discussion that we had in December 2020, where it was dedicated bike shedding session on naming, and it was successful. We decided on this naming scheme. So so now the situation is, so this one is, so meetx is an optional package, right? So it is not part of what makes standard Sage, so what is installed when you just compile Sage. And so it never was in something that we now refer to SageMath standard. So this file here wouldn't be here, but this file and this file here, which is standard, which of course it only depends on the standard package Flint, they are sharing the same namespace. They are sharing the namespace sage.matrix and the containing namespace Sage. So the Python package Sage and the Python package sage.matrix. And so they now overlap in this way. And so now PEP 420 says no init files on the path to stuff in namespaces. So when we are only providing portions of a namespace, when several distribution packages provide portions of the same namespace, and so that's Sage matrix is like this, Sage is like this, there cannot be an init file. Okay, because they would have separate init files, they would conflict somehow. What would they do? So we cannot, that's what we learned from PEP 420. So we need to remove init files. So we cannot no longer rely on init files for kind of initialization stuff for loading things in a particular order and so on. Needs to use a different mechanism. And so work already has happened somewhere in Sage 9.3. We got rid of some of use of init files to fight circular imports, no longer needed. Solve this by some other things, and somewhere here we got rid of more init files. Here we did a bunch of those. We got rid of a bunch of init files. They're not gone yet. They're just 0 bytes. So they're still empty files there because our custom build system doesn't know about namespace packages. So it still wants to see those init files. And so to complete this task, waiting for a review since 2020, is ticket 28925, which modifies our build system so that it supports such native namespace packages. Small change, and is getting tested here with something new that I haven't explained yet. It's called SageMath Object, SageMath Categories. So back to my slides. SageMath Object, SageMath Categories. These are things that are already there. They appear here. They should, let me try to find if I get matching color. It lies here as well in the packages. We have now SageMath Objects. And SageMath Categories. And it looks the same. It's just a directory. And it has a PyProject toml and so on. It has a symlink to the actual source tree. And then we are using a mechanism to only select a subset of the modules that is Python files and Python files from here. And so I've tried out various mechanisms to do so. Right now, what these things use is a very traditional thing from early Python packaging. It's called manifest.in. It selects, well, let's take a look. GitHub open already. Sage, yeah. We can take a look here. Packages, SageMath Objects, and there's here my manifest. And it just declares what is in, what is out. It says, throw away all of Sage. And it says, I want to graft in Sage CPython, which is a very low-level package. Yeah, sage.cpython something. Then I still include the init file because our build system is still not up to snuff. Sage env, Sage features, Sage structure. This is in Sage structure, we have the parent element framework and then bits, but not all of Sage categories, really just all that is needed for the coercion system to work. So what do we need? We need the categories, we need the actions, we need the hom sets, the morphisms and stuff like this. Just what is needed to barely run the coercion system, but there are certainly no a bunch of constructions here. I guess there are subquotients, there are push outs, but there, for example, there's no category of Haeckel algebras or something like this here. Yeah, so it's only the low level stuff, and a little bit of Sage MISC, a little bit meta classes, cached methods, stuff like this. And then there's a little bit of stuff that is needed because we also want to doc test these things. So it's something that will disappear. It's a work in progress, but there's some stuff that we include right now because you want to run the Sage doc tester, because the Sage doc tester is written, of course, in Sage, right? So it has also dependencies by itself. This is on the way out. There's already a ticket that solves this in a more elegant way, but you get the idea. Yeah? So I declare here in this way a nice time tested format manifest.in, some subset of packages and modules that are to be included. And that's something I built. Yeah, so, and this was a long way there because of lots and lots and lots of dependencies. Things that depend kind of semi-gratuitously on something else. So this is hard work to make, to clean this up. And we have a little guide as part of the developer's guide that explains the situation. Basically, what kind of changes need developers do in order to make things more modular. So here I explain this, the terminology, also the distinction between namespace packages and distribution packages, and ordinary packages, the ones with init files, versus implicit namespace packages. And here I explain what's in SageRoot/packages. That's what I showed you, these things that have a PyProject TOML and standard Python metadata, and so on. And then there's a discussion about dependencies. Dependencies come in various flavors. The worst ones are the build time dependencies. So they're mostly for compiled stuff, for Python modules, because what you need at build time is the development headers and the libraries that things depend on. So they need to be installed on the system, maybe in Sage Local, so that you can build the corresponding Python file. So you need the include files, and you need to be able to link it through on some platforms to the library and so on. So these are the build time dependencies. And we have done some mild cleanups when things depended a little bit too wildly on too many libraries. Sometimes these modules are often called .misc. They collect everything that's undisciplined about a particular package, and therefore it collects all the dependencies in one in one place. And so it's little refactoring that one can do to just clean this up a little bit, put things that should be separate, separately compilable into separate Python modules. In this sense, modularization in Python to some extent happens on the level of, wait for it, on the level of modules. Right. So basically, if modules are too big because they pull in too many dependencies already on the level of modules, you split them. This has happened a little bit. There are not too many places like this. But for example, really problematic module was Sage rings integer. They are very fundamental. Basically, everything needs the integers, but it was depending on lots and lots of libraries. It was having compile time dependencies on everything, on Flint, on Pari, basically everything, basically everything that's out there that has integer-like objects. We had a compile time dependency on it, and so through standard refactoring techniques, we clean this up. Basically, make things that is included directly there, change it to a function call. You need to be a little bit careful there that one doesn't impose runtime penalties. So a little bit of micro benchmarking is needed to have some confidence there. But that has happened already to some extent, and so we do have our integers without dependency on lots of packages. So William just wrote, you did a pip install SageMath objects. And yes, it's one of these packages I just mentioned. We have it up on PyPI. So Sage on SageMath dash. Where is it? Objects. There it is. Objects. And yeah, it's there. You can pip install it. Yeah, it only depends on very little. It depends on GMP. It has a dependency on GMP Y2. Let's take a look at it, what it looks like in the source directory. Where's my GitHub? Here. So I showed you the manifest.in, and let's look at the PyProject TOML. This is not an honest PyProject TOML. This is a template because I like to generate these things using a microprocessor so that I don't hard code versions in every little metadata file, but the versions are coming from a central place. So it makes things much more maintainable. And so I'm using, so because I refuse to learn Python templating systems that may be current, I'm using something time tested. I'm using the M4 macro processor that has been around since the 1970s. So tested and available in every system. So it looks a little bit funky, but that gets the job done. And so in this way, we are declaring build time dependencies. We are saying the build back and the setup tools, and then we have requirements at build time on setup tools, some other stuff like this. We have this our own build system Sage setup. We need Cython at build time, and we need GMPY2 because it provides build time stuff, the PXD files, the Cython headers, and sci signals for the same reason, because we need the PXD headers that are shipped with it, and that's what is needed. We also do need the GMP headers, so they are not shipped, unfortunately, with GMPY2. Yeah, so that's something that's still extrinsic. Yeah, so it's still something that needs to be. So the dev headers, we still need them. So it's not 100% pip installable on a naked system, but almost. Yeah, so you need GMP headers, and then the rest is declared here. Yeah, so as I said, yeah, so there's no way to declare in Python metadata as of now that system has a dependency on GMP headers. Okay, and then what do we have? Setup CFG, also not. So setup CFG is a standard Python format. M4 is again because it's macro generated and has splice in some generated stuff. And there's still a bunch of boilerplate here that is copied, and that I also want to actually make macro generated for more maintainability. Like here, a list of Python versions, not current. Yeah, so that should be auto generated soon. So yeah, this one is also wrong. It will be fixed soon. And so here this declares the runtime dependencies. So at runtime, I don't need setup tools. Yeah, so it doesn't appear here. At runtime, I do need Cython for whatever reason, because we do have a module called sage.misc.cython that makes runtime compilers available. We will, and it's also, that one is used for doc testing, for example. So right now it's here because it's a requirement for doc testing, because we have a runtime use of Cython and of the C compiler to doc test certain Cython components of Sage. So it's declared here, will be cleaned up later. But the real dependency is GMPY2 needed at runtime. So sci signals also really needed at runtime. Package config, that's again, we need it in conjunction with Cython for doc testing. Okay, and a bunch of scripts, selection of the familiar scripts that you find in bin. Currently in, I packaged them here in SageMath objects, and William installed it. Thanks for all the Europeans. I know it's getting late. Talk will be is recorded, and we'll make it available. Thanks for holding out. So let's see. So we have here a bunch of those scripts. So William already has them on his computer now, because they're installed in the corresponding bin in the VM or wherever he installed things. And yeah, that's SageMath objects, and it can do some stuff. It is not very thoroughly tested because, and so going back to the little manual here, we have, okay, build time dependencies. Runtime dependencies, yeah, they declared in install requires, as I just showed you. So basically everything that a Python module imports at the top level, yeah, so basically which needs to be importable at import time, well, needs to be there. It needs to be declared as a dependency. Otherwise, you can't load the modules that have this dependency. Yeah, so that should be declared. And so these kinds of dependencies, we can fight them by delaying those imports by various mechanisms. And so here are several things, some guidelines that I've written here that we have already used in many ways to get modularization going. There's the Sage package all thing. Yeah, so the all is a Sage specific thing that provisions the global namespace. Yeah, the global namespace of Sage has lots and lots of bindings for convenience. This is what you're getting when you type. Yeah, type anything, any of the built-in things. It somehow comes through imports from such .all modules. That's great, but there's also library use of these .all modules because it's easier to type from Sage rings .all import ZZ. The problem with that is it also pulls in lots of these other things that have that we want to have at the global full-featured Sage namespace at the Sage prompt, but not everything that imports ZZ also needs the periodic rings or needs the function fields or anything. Yeah. So that means we need to get rid of library uses of .all whenever we are importing from such namespace packages. Yeah, so whenever we have something that such that portions of it are provided by different distributions, yeah, so no init file, then we shouldn't be importing via .all, yeah, because it's an immediate obstacle to modularization. And so that's really easy to do. It's a meditative exercise, or can be scripted to replace these things by more specific imports. We've done a lot with in this direction, where you have got the ticket. A lot of tickets can see that to do the .all thingy. So here was a series in the 9.6 series, got rid of some .all imports, more .all import, stuff like this. Yeah, easy to do, easy to contribute, spot them, fix them. Yeah, so then here. Sometimes things are imported at module level, but are only needed in one method. Yeah, like for example, in combinatorics, lots of things are purely combinatorial, but some things put out some generating functions and need to use symbolics. So if you imported symbolics at the module level, it means that the whole module will depend on maxima and on embeddable common Lisp and on this and on that, on singular and so on. If you move this thing to the method level, yeah, imported, and imports are super fast in Python 3. So it's not really, unless you do this in like a nanosecond level, you know, in a loop, there's basically no cost in doing method level import. That's just way how we can get rid of module level imports. Yeah, and then we have a module where there are some optional features. Yeah, there's some methods provide some of the functionality of a module that needs additional dependencies. Well, put them there, and we declare them differently. We don't declare them as an install requires, but there's a different Python mechanism that's called here other runtime dependencies. It's called extras require. So we can, for example, say, you know, we want, what's my example here? I want Sage math coding, maybe coding theory, and we want the bits that depend on symbolics. Yeah, so that's a syntax here. You can do pip install with the square brackets, and that pulls in such extras. Yeah, and this way you can declare without having to know more of these nitty-gritty details. of what libraries that involves, you can just say, well, I want the symbolics flavored coding theory as well. Same thing for combinatorics. You can say, I want to do pip install sagemath combinat with the symbolics. If you just want simple combinatorics, if you just want to compute some binomial coefficients, right, you don't need it. And so that's another way to remove such dependencies. Use method level imports. We also have lazy imports. Lazy imports through Sage homegrown implementation. Lazy imports are also coming to the Python mainstream. There's a currently PEP for bringing this to probably Python 3.12 or so. Waiting for it. We'll see if it's usable. Then here's one thing. It's rather interesting. Object-oriented design dictates that one should never use instance object class, because it's of course it means that you made some mistake somewhere in the class design. Nevertheless, in practical object-oriented code, we do oftentimes have to do instance checks, so lazy imports, we do have quite an investment into lazy imports as well. That's a great way to when basically this one here is not feasible. Method level imports, because we have too many methods using that, or there's too much overhead by that. We can do the lazy imports, also very nice. And also a lazy import is nicely integrated with our feature system. Basically, lazy import, when it doesn't find the module, it can also tell you what packages you can install using pip, or perhaps even using your Ubuntu package manager in order to get that functionality. So we have this kind of user informing user education department of Sage that tells people what to install. I think very important, to counterbalance the modularization. Of course, so modularization does create extra friction, as in, you installed some little things and then you run your computation and suddenly something is missing. So what is it? What module is missing? And so we are also investing into the corresponding information system to also, tell the user what's missing. So it doesn't have to guess or have to be an expert in these things. Here's an interesting thing that I want to mention. So, okay, say we do have these instance thingies, or something even older. There were Sage-specific methods that are like this, like is periodic field and so on. And so these kind of create a kind of like a modularization anti-pattern. It's a little bit like this. Where is the class coming from that you are testing from? Well, it's coming from the implementation module of that class. So you want to know, is it a periodic ring? Well, that periodic ring is provided by something that has a compile and runtime dependency on NTL. So how can I import that thing to test whether a given object that came to me is an instance of it? I need to have it available, otherwise it's an import error. And so this pattern was widely used. Widely used in the Sage library. Basically, you import a module just to check whether an object that I have is an instance of a class provided by that module. And so that's really bad for modularization. And so what we now have is for various rings, at least, we have abstract base classes that are specifically made for such is instance testing. So the ABCs, they can be imported without any dependencies. So we have Sage rings ABC. So now we can do is instance of object of Sage rings ABC periodic field. And so these base classes, so they are not in competition with parents and categories or anything, but they're in a one-to-one correspondence. We doc test this actually, that they're in one-to-one correspondence to an implementation class. Because we don't want this as a mechanism that somehow makes the our kind of competes with our existing abstraction mechanisms of mathematical categories and so on. But it's a modularization mechanism, basically to do instance testing. Don't use those is_ methods. We're deprecating all of them. Don't use is_instance with a concrete implementation class that will have heavy compile and runtime dependencies, but rather do an is_instance with an abstract base class. And so a lot of that has happened. And we also have something else not very widely used yet. This is something that extends the lazy import mechanism. So so here's an observation. If there are no aliases and re-imports, so the following is true. That's the semantics of Python. If the module that defines a particular class is not loaded, or if it cannot be imported, there cannot possibly be an instance of it. So if I want to check is something an instance of a particular class, but that class is coming from a module that is not present, either not loadable or not loaded yet, then this instance should be able to say false without loading it. And so this is something that we can do here with lazy imports. So the lazy import proxy objects know how to answer is instance. And so various mechanisms like this, we're still trying this out a little bit. What is good, so what is fast in what situations and so on. So there are various, there's not like one thing that fits all, that there are various implementation techniques that we can use to basically make dependencies lighter and use whatever works. And finally, there are doc test only dependencies. And so here's the thing that I brought up before, I wasn't quite ready for it. So SageMath objects, we can't really test it as a self-contained Python distribution, because many of the tests are written in a way that the objects that we test the various mechanisms on are defined somewhere else, in something much higher level. So, for example, we are testing maybe that our meta classes work correctly by testing it on, I don't know, on affine Haeckel algebras. And so basically, for testing, there are much heavier dependencies in order to get full test coverage. And so we have a way to actually deal with it. We have annotations for doc tests. So in the same way that already optional packages, like for example, when something depends on optional package meetx, we are marking this sharp optional dash meetx, and it's only tested if that library is installed. In the same way, we can now restrict certain doc tests also to the presence of certain Python packages. So this is keyed to the namespace packages. Now, for example, to sage.symbolic, doc tests are marked like this. So this, again, it's busy work, basically looking through the doc tests, see what fails when I just have SageMath objects installed, and then using editor macros to put in lots of sharp optional things. Something that one can do, in late night work when the theorems, the theorems are resisting, proofs are not coming along. One can do this kind of work. Basically annotating doc tests. What doc tests really depend on higher level facilities, and yeah, so we can do this. Some of this can be automated. So let's look at a few of those tickets. Something like this. Sharp optional. Yeah, here. So for example, stage geometrical hedron, we most people only need rational polyhedra, but we also have polyhedra over number fields. So I am working on a distribution package called SageMath Polyhedra that only deals with the rational case, most common use case, fewer dependencies, and so on. It's the wrong ticket. This one here. Yeah, this one here is the good one. So let's take a look at the changes. I hope I'm screen sharing. Yes, I am screen sharing. Otherwise, this whole talk, I did this once when I taught a lecture. What do the changes look like? Well, this one is on top of some other tickets. So yeah, anyway, so here are the actual changes. I'm not sure if you can see it. It's just taking a bunch of doc tests and marking the ones that, for example, try out plotting, marking them with sharp optional sage.plot. Yeah, so it will only be tested if plotting is installed, because what does it need? It needs matplotlib, it needs floating point numbers and stuff like this. And okay, how are these changes? Well, obviously with stream editor. Yeah, so everything that calls a plot method, I marked up like this. Then I tested this in the restricted distribution that only has sub portion installed. And sometimes there's a follow-up error because some doc tests depends on something previously that I've now disabled or only run when plot is installed, and then fix up these manually. Easy work, easy iterative work. Just add these annotations. That's sage plot, and then so here the ones take some of the interesting classic polytopes. Take the dodecahedron and these number fields. Yeah, okay. Mark it up with sage rings number field, and it's work like this. It's not very interesting work, but it's it's work that one can do in nothing else when you can do nothing else. And so in this way, we can do two things. We can figure out, first of all, how do we make something so that it passes tests, but we can also figure out perhaps whether we have enough doc test coverage without depending on higher level facilities. And so perhaps we can use this as a teaching tool, onboarding with students who want to learn about a certain facility, to write new self-contained doc tests that depend on fewer things. Also, that's in my experience, is a great thing to get students started on a doc testing centric workflow by first documenting existing code before getting into the game of writing and documenting and doc testing new code. So it's possible that one can use training activities, to make progress in these kinds of things. Also. Yeah, those are the doc testing dependencies. And yeah, we have infrastructure for testing these things. There's a wonderful classic Python package called Tox that creates basically disposable virtual environments that is just made for such tests. Yeah, so you don't need to make your separate Git clone of the repository for doing modularization work. You can just use your ordinary work tree. Modularization, as I said, happens behind the scenes by writing such manifest.in files that just pick and choose, and then you can use Tox to have things automatically compiled and tested. It doesn't mess up your normal installation. So it's not like we need to go in and mutilate your Sage installation, but we can just install things on top of, here's, for example, the line for SageMath objects. As what do? You do the bootstrap so that the build scripts are in good order. And then you just use your existing Sage. You go into the Sage shell and you say, let's switch into that Python source tree. And then let's run Tox very verbose with the environment. Sage Python meaning compiled with the Python that is also in use with Sage or same Python version. And then it just, it builds the wheel and it runs the tests and you see the error messages and you can make adjustment to your code. Yeah, so it's all automatic and very convenient to do these things. And yeah, that's where we are. So that's a preliminary hierarchy of distribution packages. We have objects, we have categories on top that provides then all the categories with, including those affine hacker algebras as a category. And then there's something called SageMath environment that kind of knows about what's going on in the system. It knows what software is installed and so on. Then there's SageMath REPL that provides the Sage language, so a pre-parser stuff, and builds things together. And then we have various topical collections and so on. But overall, it all goes into SageMath standard. This is where I stop. Thanks all for attending. I know it's late in parts of the world, and I'll be happy to interact more on these things. Lots of tickets that need review and help and interaction. And domain experts need to help with designing the meaningful libraries. Yeah, so what distributions should we design? Does it make sense to have one package SageMath Combinat, or should there be something like algebraic Combinat and analytic Combinat? Who knows? I don't know. I don't do these kinds of things, and so help by domain experts is needed to bring these things in a great user-friendly shape. That's where I stop.
Do we have time for any questions, or do people have to go?
I have plenty of time. I'm here.
One tiny question, which is, do you think all this stuff you're doing could have a positive impact on the Sage startup time?
So far, it is neutral. I think mostly by using more lazy import, one can quite easily reduce startup time. But I'm not particularly bothered by the startup time. So on the order of a few seconds. So something like SageMath objects, it starts instantly. Basically, it doesn't load anything. But it's also not very useful, right? And so, so finding the right compromise about what should be loaded up, it's I think relatively easy just by changing stuff from import to lazy import in some Sage.all files. It boils down to a matter of just wanting to do that, and I don't think there's any technical difficulty regarding this. It's not something that I'm working on. I don't think it's very I don't think it's very difficult more questions, comments?
So yeah, go ahead, Dima.
I just wanted to understand that picture that on the last slide.
Which one?
No, I mean this the hierarchy of two distribution packages. Is this not complete in some sense?
This is far from complete. Yes.
Okay. So, yes. So this is more of a project in some sense, right?
Yeah, it's evolving. This one. So this one is slightly more detailed already than what is merged. This is based on one ticket that introduces distributions called SageMath environment and SageMath REPL. Basically, this ticket is making SageMath objects very clean. So basically, what I mentioned before, these kinds of things that were in there for doc testing purposes, they are no longer in there. For doc testing it, one installs at runtime also a SageMath REPL, which contains, so for doc testing depends on the Sage language, so the pre-parsed language, and the various things that it needs the integers and so on, so it needs the SageMath REPL for it, but it's only needed at runtime. So these facilities are not needed at compile time of SageMath objects, and it's also not needed at runtime if you don't want to doc test SageMath objects. So in that ticket, I make this one here very clean, and also I'm making the SageMath categories cleaner. So it really actually depends on SageMath objects instead of duplicating what's in SageMath objects. And then I have SageMath environment, which it contains everything that's kind of builds the connection to the installation, such as it knows about the sage.env, it knows about the features that are discovered at runtime, so sage.features and so on. So kind of what I have over there here, SageMath object, SageMath categories. This doesn't have to know what is installed in your system. So maybe it was needed at compile time, but at runtime, this doesn't care. It doesn't care what you have installed in your system. And so that's this separation here. You have the things that depend and the things that don't depend. So I'm making these things clean in this way. So SageMath graphs, for example, depends to some extent on what optional packages are installed, because, for example, it has some graph libraries in there. So for certain features, at least, it depends on what is installed. SageMath graph doesn't exist yet, except there's a ticket that promises to make it.
There is a considerable amount of code in combinatorics, which is not clear to me how it fits in this picture. So there are sort of combinatorial objects which I don't really see here. Yeah. So SageMath Combinat, I have a ticket for it. There's no code yet, and so that's where I'm really hoping for input from discussions with domain experts. Basically, where do I put my discrete mathematics? So there's namespace Sage Combinat, there's Sage.coding, there's Sage.graphs and Sage.matroids and so on. So I don't want to be the person who decides for now and forever what goes into what distribution package. So in the ticket that promises to do Combinat, let's bring it up. I have it here somewhere. Here it is. I went a little bit through it and looked for kind of the hard constraints. The hard constraints are the compile time dependencies on libraries. So you go through the modules. What does it use? Okay, here. Sage, it is in alphabetical order. So binary recurrence sequences. Well, what does it need? It needs, for some reasons, number fields, finite fields, and Sage.functions, because it needs logarithms. I'm not quite sure whether it really needs symbolic logarithms or whether it needs numerical logarithms. Didn't check. Someone has to check, and then one can find out. Does this have a real dependency on Sage symbolics? Does it have to work with a symbolic ring, or is this really just is it something like an optional dependency, or just some method that needs that? Should it be an extras require? And so on. So I went through here. Finite state machine uses Sage symbolic. And again, I haven't noted, I probably knew when I went through this. What is it? So one needs to, I need to go through it. It's not automatic. So one needs to have a discussion there, and people who use these things. So for example, I never use analytic combinatorics. So yeah, so here, easy ticket. Plain partition py needs sage.functions.trig, and therefore the symbolic ring. But it really only wants to do plotting. It needs sine and cosine somewhere. So it can probably be rewritten so that it just uses Python built-in math.cos and sin. Yeah. Instant modularization. Yeah, it removes the dependency on singular and maxima. Yeah, and so it's these kinds of things. Yeah, where basically, you know, kind of automatic use of you know, what we have. You know, oh, I want to use a function, so we have to import from stage.functions. Was a little bit too coarse-grained, and so this is now in easy cleanup tickets. Yeah, we can simplify this. Yeah, and so this doesn't require very deep insight. It's testable. Yeah, using what's documented already as a methodology. With talks and then we can make design. Yeah, so where should things go? Yeah, how to split things up. Some of the work is already done. I've designed some. So going back to, no, it's not the right thing. Going back to this diagram, I've kind of yeah. This diagram is very incomplete. So on the top is Sage Math standard. It's not everything. It's just everything that's standard. This one here is stuff it provides tree decomposition algorithms for graphs. Optional package, not part of Sage Math standard, but it would be like Sage Math, everything that would be like on top of everything, maybe could be a virtual package. I have here one package. There's that's provided by a ticket that's still under construction. That's called Sage Math Standard No Symbolics. It's more like a strategic package that's for chasing down kind of gratuitous dependencies on the symbolic ring. So basically, it cuts out the symbolic ring, Sage symbolic, and Sage functions, Sage calculus, Sage manifolds, and then one can just check, you know, you know, what in Sage.combinat still works. Yeah, and so in this way, by running the test for it, we can basically make progress in these simple fixes in downgrading dependencies from compile time to runtime, downgrading from module load time to method call time, and so on. So this basic refactoring is testable with respect to imports from the symbolic ring using this package. Yeah, and then complementary to that would be Sage Math Symbolics. There's a ticket for it already. It would just be you know, kind of the minimal things that we need for doing like SymPy-like symbolics. Yeah, a bit of symbolic math manipulation, a bit of integration, a bit of this and a bit of that, but no hacker algebras, right? And no modular forms probably, and therefore no heavy dependencies. So maybe no Flint, maybe. Although right now our symbolics depend on singular for a very obscure reason, because our PyNAC, which is our kind of low-level symbolic manipulation package, depends on a singular library for doing factorization of polynomials. So that's why symbolics packages right now depend on full-blown commutative algebra package. Probably easy to fix, for example, by making this dependency for this factorization not go through a C++ level link, but going through a Python function call. Easy to fix. There's a ticket for it. Someone needs to work on it. Someone who knows Python. Best case. And then so then we can basically split off this chunk. Then, you know, basically this arrow here, Sage Math Singular to Sage Math Symbolics, can go away, and we can kind of build a lightweight not quite as lightweight as SymPy, because we do still have compiled dependencies. Yeah, we do have our ECL, we have our maxima in there, and maybe some other things. But maybe it's just 100 megabytes, not 15 gigabytes. Yeah, something that becomes usable becomes when SymPy doesn't cut it because its integration is too slow. Maybe people can tap into 40 years of Lisp-based symbolics with maxima and axiom. Right, this is what Sage, of course, can provide. Yeah, but we will be able to offer it without the whole 15 gigabytes of heavyweight package. And in terms of strategy here, so I have here this thing, Sage Math Standard No Symbolics. Below it, there's a lot of room for subsets. Yeah, so might be a package that maybe does the, I don't know, coding theory. Yeah. Maybe everything for coding theory, or maybe everything for, you have your SageMath polyhedra. SageMath polyhedra and SageMath categories. There's probably stuff that fits in between, because in the polyhedra, I do need polynomials a little bit. I do need the rationals. Right, the stuff in between. It's not designed yet, but help is needed. Right now it's in SageMath polyhedra, so I have basically the minimal things. There's one library, one polyhedra computation library. There's a little bit of this and a little bit of that to make rational computation possible. Easy to install with pip. It's already there. It doesn't really work yet, because some of the some generic algorithms for linear algebra are missing, and only specialized algorithms that need the Flint dependency are implemented. So currently, to make it useful, one does need Flint. But clear that everyone who wants to do polyhedra in dimension 4 really needs high performance arithmetic with Flint. It's great that it exists and we love it, but it's not clear that this is the best kind of deployment route for a package that wants to reach a maximum audience for polyhedral computation. If it if a Flint becomes pip installable, for example through maybe project that both Sage and other downstream users of it that are in Python can use. Then if then we use cibuildwheels to actually make it pip installable as a wheel, then we're in really good shape. Yeah, then we can also have a pip installable Sage polyhedra that makes use of fast arithmetic and fast matrix stuff using Flint. Yeah, but so there's work needed on multiple levels, packaging, not just the packages that are under Sage's control, but also things in the interfacing world. Yeah, so where are the Python interfaces that are reusable and come with a solid deployment infrastructure, so wheel building, cibuildwheel, and so on.
So this is maybe a little bit more general, but so the doc tests have both like a sort of pedagogical purpose as well as testing, executing the code. Have we thought about having non-doc tests where we can put in tests that don't serve a pedagogical purpose, but mainly exist to exercise the code? And for that, we could make, have more restrictions on what they can depend on.
Yeah, so we already have, you probably remember this, there's already a variant of the examples tag. There's also a tests tag that at least does not show up in the formatted documentation. So that's already a place where this happens. Also, the Sage Combinat people, they introduced this test suite business, which so you have these underscore test methods that do exactly that. So they're inherited. So basically, in subclasses, you still run the same tests that you defined for the base classes. So that's the next mechanism. And also there's work underway to bring the use of mainstream Python testing via PyTest to Sage. So Tobias Dietz is working on this big time. So I'm not sure if we'll talk about this tomorrow, but there are a number of tickets that basically do PyTest stuff in conjunction with our existing Sage-specific things. So we have a little bit of that already in. Let me show you. We have it here. Sage Math Sage. So in two packages. So source Sage numerical backend. There's a little bit of that. So these are the linear programming backends, and there is already a little bit of PyTest stuff. So there's here glpk backend test.py, and this uses a PyTest. It also has here test fixtures, whole stuff like this, and you don't see much here. It's just a little bit kind of I volunteered the Sage numerical backend stuff to undergo some PyTestery. So they sacrificed this to the PyTest. So Tobias Dietz did basically converted some of the things that we had in Sage specific things to some PyTest stuff. Generic backend test is where the actual test methods are defined. So there's just a little bit. So there's like a test, that's one method, a number of columns, returns something non-negative, right? And so one can write these things already in PyTest if one chooses to do so. Another module where this is already in use is what Tobias Dietz did, is Sage manifolds. Somewhere here in the differentiable manifolds, there's look for something that's something test. Symplectic form test. This has a little bit of testing with PyTest.
Cool, and those get run with Sage-T?
Yeah. So when you run Sage-T, you at the end it also runs PyTest. And we fixed some of the annoyance that was there for a few versions where it was complaining a lot. It's now clean, and so it runs these things automatically. And so there's work on the way. So there's also work to actually be able to run the Sage doc tests via PyTest. This has the benefit of IDE integration. So basically, if you do VS Code, you can now I'm not sure if the ticket is merged already, but you can just see things, have the IDE support. And so these things, I suppose we don't really have that yet, but I suppose one can also conditionalize these things and the presence of features. I don't think we have done this yet. So right now, everything that's conditionalized on modules or optional features, this is currently done with doc tests, but I don't see an obstacle to doing so. More questions, reactions, comments?
Yeah, if not, I'll just close the session. I'll be around on the Zulip and be happy about any interactions.